You get it? All right. I'll begin. Heavenly Father, we thank you for this day. Again, Lord, I thank you for the students. Just pray you'd help us to understand a little bit more about Greene's theorem and just glorify you, Lord, in what we do, Lord. In your name I pray. Amen. Okay, so actually, I'm introducing a new concept right now, which you probably haven't seen. And yet another interpretation of the line integral, actually. And so here is the definition. The flux of F, in this case we're talking about a two-dimensional vector field, PQ, through a simple curve C. Now, mathematicians take great pleasure in giving technical meanings to words like simple. So simple curve actually means that it's a curve which appears as the boundary of a simply connected region. Say, what's a simply connected region? Well, it's a region without holes. It's a region for which there's a clearly defined inside and outside. All right. Anyway, it's a simple curve, which you'll know it when you see it. Anyway, so here it is. So suppose, for example, a circle is a simple curve. A closed loop, simple curve. All right. Suppose F is continuous. On an open set containing simple curve, well, let's call this containing C, all right? Define the flux phi sub C equal to the integral, and again, this is a closed thing, so we use this integral with a circle through it to emphasize that we're looking at like a loop. And then here it is, F dot n hat ds, where n hat is the outward-facing unit normal to C. Now, so I think a picture is in order. Something, well, anyway, so C could be something like that, for example. So there's clearly an inside and an outside to C, right? So let's picture what we mean. Let's picture what we mean by this n hat. The outward pointing unit normal to the curve. So start here, be like that, right? Then like this, like this. These are supposed to be the same length. I may or may not be successful in my maintaining the length of my purple vectors, but I'll try. So after I get done with this, we should have something that resembles a thing you might learn about in biology, right? For me, it was about the 5th grade last time I studied one of these. Was it the Golgi body or the, what's the thing called? I forget, I don't know. Or an amoeba. You know, these little hairs on the outside, they move the thing along through whatever. The cilia, yeah. Wow. Words. It's very relaxing, really. Oh, the ways you guys would find to misinterpret that question. The ways. There's just no telling. If I gave this as a question on a test, so the right answer to that is like done. But so anyway, I pictured n hat, right? So what is f dot n hat here? What does that do for you? What is this? This is equal to the component of f, right, in the n hat direction, right? And what is that times ds in terms of interpretation? Basically, this is the number of field lines cutting through ds. So I haven't pictured the field yet, right? Let me picture the field for a second here. Suppose the field got like some kind of source here and here. I don't know, so maybe this is a plus and this is a minus, right? And so we get like a dipole field, you know? Something like that. Now I've made a mess of it. But the point is, these field lines are going this direction, right? Draw some arrows in here to remind us the direction. So depending on whether the field line, you know, how it hits the, see, for example, this is, I'm thinking of it as electric field line, but this like electric field line, as it cuts right through here, it would give no flux. See, because it's just tangent. This, I haven't drawn it, but if I were to draw one more here, it's like hitting that tangentially, so that doesn't count as flux. What does count as positive flux here? Like, oh, for this one. See, that field line is lining up with the unit normal there, so that would count as a line, like an honest-to-goodness line. Like over in here, if I was to draw another one, you know, like here, that probably wouldn't. Sorry. Anyway, that one wouldn't really count as flux because it's tangent. So to cut through means that you have to, when you go across, it's how much you line up with the unit normal, whether or not that line counts. You know, to give one that counts. Everyone counts. Something like this, right? So the flux here is going to be, you know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, 14. I can't count. 14 times 14 lines times the circumference of the circle would give you the flux, right? Then you have to decide how much each line counts for in terms of your units of flux. I mean, how much that should count for. That's a question of physics. What system of units do you choose? How much is each line worth in your picture? All right, anyway. But anyways, so this is the idea. Flux is the number of field lines that are really cutting through the curve. If it goes tangential, it doesn't count. Here it counts completely. All right. So, great. But how do you actually, I mean, it's a lovely formula. How do you actually calculate that? Well, now I've made a mess of it. I'm going to have to do it over here. So if I look here, right, suppose and I want to think about counterclockwise. So I'm thinking the orientation of the curve like this, counterclockwise oriented, right? So let's let this point be at, you know, x comma y, right? So this vector right here would be what? It would be dx ds, dy ds, right? The tangent vector. How do I get the outward normal? I want this thing, right? What is that as it relates to this? I mean, you got really two choices, right? The dot product of these two things has to be 0. So let me just write something down and see if it works. Let me try dy ds comma minus dx ds. Does that make sense? I mean, definitely the dot product of the black and the purple vectors are 0, so they're 90 degrees apart, which makes sense, right? The tangent and the normal should be 90 degrees apart. Do I got the signs right? Like, let's see here. So, look, this has a dy ds, which is positive. This gives me a positive x component. Here, the x component's negative, but the y component of the purple is positive, so negative, negative. I think that makes sense. I think that's it. All right. And so, in other words, the unit normal we can get from the arc length parameterization of the curve as simply dy ds comma dx minus dx ds. How do I know that that has length 1? If I parameterize the curve with respect to arc length, right? What can you say about the unit tangent? Well, I mean, this is t, right? I mean, what's the speed if we use arc length parameterization? The speed is 1, right? It's a unit speed. So the unit tangent is the velocity vector, is the point. So anyway, I can be sure that that's a length 1 vector. And so then we look at the flux. What do we get? So we're looking at what? P comma Q dotted with dy ds minus dx ds ds, which works out to the integral of p dy minus q dx. So that calculates the flux through a closed curve. So it's not a direct interpretation. I mean, we've talked about the integral of p dx plus q dy, right? So here's the distinction, right? Integral of p dx plus q dy over a curve C would equal to the work done by f equal to p comma q around C. This is also known as the circulation of f along C. Because if f is a velocity field and you take the line integral of f around the curve, you're actually counting how much that velocity field is lining up with the curve. That's the circulation of the velocity around the curve. So this is also known as circulation. What we've just worked out, or at least motivated the definition of, I hope, is that this related but different line integral around the curve, p dy minus q dx, is again the flux. It's the number of field lines cutting through C, up to some convention on how you count field lines. All right? Let's do an example. Let's actually try to work out the one I drew the picture of, which is really nice, the radial vector field. Let's look at f equal to, let's say, 1 over the square root of x squared plus y squared, x comma y. Oh, that's not what I want. I want 1 over x squared plus y squared, x comma y. So there's a vector field. Let's calculate the flux of this guy through the unit circle. And let's be a little bit greedier. Calculate flux through CR, which I'll say is x squared plus y squared equals to r squared, counterclockwise. So the counterclockwise oriented unit circle, not unit circle, but circle of radius r centered at the origin, right? So here we go. We're supposed to calculate the integral of p dy minus q dx for this thing, yeah? So that's the integral of c of what? What's my p and what's my q for this example? Yeah, p is, I heard x over x squared plus y squared, and q is y over x squared plus y squared. So we're looking at what here? We're looking at x dy minus, looks like y dx over x squared plus y squared. Well, this is embarrassing. All my examples are the same example. We did this yesterday. Here, I'll work it out again. X equals to r cosine theta. Y equals to r sine theta. I'll use a new letter to make it seem fresh. So dx minus r sine theta d theta. dy r cosine theta d theta. So what we got here, we got integral from 0 to 2 pi of r cosine theta d theta minus r sine theta d theta, well, minus r sine theta d theta, blah, 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 x squared plus y squared, also known as r squared. So what we got? Integral from 0 to 2 pi of, well, d theta, also known as 2 pi. Which goes back to my assertion that, in fact, the flux of the radial vector field through the unit circle, through a circle, it should be something, yeah? We can understand this a different way. So essentially, what's the magnitude of the vector field? If we look at the circle, radius r, right? And you look at the vector field f anywhere here, what's its magnitude? One over r, right? The magnitude is the reciprocal of r. If we look at plugging in the circle, we're looking at a point which is distance r from the origin divided by r squared, so the magnitude is 1 over r. So the flux, in this case, it really is the magnitude of f times the arc length, which in this case is 1 over r times 2 pi r. Now you can't usually calculate flux by just multiplying arc length times magnitude, because usually vector fields have variable magnitude over the curve, and the direction may not always line up with the normal to the curve. This is a rather special case that we can just multiply the magnitude times the arc length to get the flux. Yeah.
How can the flux be a decimal?
Be a what? Well, again, this is up to your convention. Maybe every line is worth pi worth of flux. Every line counts as pi. If this was actually an electron, you might have maybe 1 line per electron. Something like that. That's a question of physics, how you want to count the lines. But anyway, all it really, it's a qualitative thing, right? So what you can say is that the density of lines speaks to a larger or smaller magnitude of the field. The fact that the lines are more densely packed close to the charge tells me that the magnitude of the electric field is higher here, and it's weaker out here because the lines are more separated. That's all I can really directly read from field line things. unless you're very dogmatic and you set a specific meaning for each line, which you could do in context, but is not commonly done in textbooks. Like if you look at a textbook and you're given a problem in physics and you look at the field line diagram and it's got like 20 lines, it's probably not the case that the author wants you to go 2.7 microcoulombs. Like that's probably not the intention of the diagram. It's just for illustrative purposes. Okay, so that's flux in a nutshell. The interesting thing is, we were talking about Greene's theorem last time, right? So what on earth does flux have to do with Greene's theorem, right? So what I'm going to show you now is that there is this beautiful connection between the flux of a vector field in the plane and the so-called two-dimensional divergence. What's the two-dimensional divergence? If I wanted to define the divergence of P comma Q, what would you think it would be? Whee! So, may I submit that the two-dimensional divergence should be the divergence of P comma Q is partial P partial X plus partial Q partial Y. Does that seem like a reasonable definition for the divergence in two dimensions? I mean, so if you have 3 dimensions, you just add partial R partial Z, right? Well, I will soon, here, I need to fix that. There we go. I always forget to zoom out when I use the camera at the end of class. And then all of a sudden I go back and look at it, I'm like, oh, everything's out of frame, you know? It's like, idiot. Me, not you. It's you guys. I mean, I don't pay you a lot to do this camera work. I mean, points, I suppose, but how much are they worth? A lot. A lot? Oh. No one gives me money for them. I don't know. I'm not asking for bribes, to be clear. Am I? You could bribe me with genuine interest in mathematics. That's the one bribe I will take. Okay, so sorry, I'm an idiot. Okay, so anyway, we just went through this. This is the formula for the flux. So essentially, this is what I've just derived heuristically, is that we can calculate the flux by doing this corresponding line integral. Great. And that brings us to this kind of surprising discussion. So here's the idea. We're going to look at a little rectangle, all right? And we're going to try to decide what is the flux of this vector field f, which we could write as px hat plus qy hat. What's the flux of this vector field through this little rectangle? Okay? So we have to, to calculate the flux through each side, we just simply have to calculate what's the component that's actually piercing the side, lining up with the normal, right? And then multiply by the length of the side, because that's how we get the flux. So let's see here, to start with the top. In the top, we have q pointing up. The length of it is delta x, right? So I'm assuming we got xy, x plus delta xy. So we're looking at this little, the width of it's delta x, the height of it's delta y. So anyway, the flux through the top is just q. Well, q what though? It's q of x comma y plus delta y. See, because up here, I mean, you could, I guess you have a question is like, do you want to use Q from this side or from that side? I decided that I would use that side. So it's, or excuse me, this side. So Q of x plus y, delta x. Now, this formula is already not quite accurate, right? Because Q could in principle change going from here to here. But you know what? At the end of this discussion, we're going to take the limit as delta x and delta y go to 0. So it doesn't really matter which corner I use to set it up, all right? If it bothers you, you could use the midpoint. You know, that would be better approximate, whatever. Anyway, so to a good approximation, this is the flux through the top. The flux through the base is f dot minus y hat is the normal to the base, right? So that picks up minus q xy delta x because we're down here. We're at the xy. So I use xy to find out the value of q and multiply by delta x. That's the flux through the bottom. The left side, well, the left side I've got a normal. It's pointing to the left, right? Am I correct? So the normal will be n, if you will. N hat is minus x hat here. So f dot that delta y gives me minus p delta y. That's the flux through the left side. The flux through the right side, I've got delta y is the height of it. X hat is the normal to the right side. And so we pick up p of this x plus delta x comma y delta y. Any questions about this so far? So what we have here is the total flux through the little rectangle is the sum of these four fluxes, right? And what does that give us? So the net flux is phi, I call it phi r because it's a rectangle. And it's the sum of these three. I grouped the delta x's and delta y's. Then what you can do is divide by the delta x delta y. And when you do that, something really shocking happens. You get the change in, you get q x fixed, y plus delta y and y here, divided by delta y. And over here, notice the y is fixed, but we've got x plus delta x and x like that. So in the limit as delta x and delta y go to 0, that's the partial derivative of q with respect to y, and this is the partial derivative of p with respect to x. And so we get partial q partial y plus partial p partial x, which, by the way, I was just advertising to you, we should think of as the two-dimensional divergence. So what does this mean? This means that the flux, right, the flux per unit area is apparently equal to the divergence of the vector field. So divergence has something to do with flux going out of an area. That's what this calculation shows. And then, we just, integrate this density over a finite region, and we find the net flux through the region. There's a significant jump right here, which I better argue with a picture in the next page of the notes, okay? But somehow, when you take a region and chop it up into little rectangles, chop, 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 and then add the flux over all those little rectangles together to get the net flux, it works out to the, of course, the integral of the flux over the area, which is, by the way, the divergence. And so that is what's known as the divergence form of Greene's theorem. It says that the integral of the flux of the vector field is equal to the integral of the divergence of the vector field over the area. This was not the Greene's theorem I wrote down last time for you guys. What was the one I wrote for you guys last time? Do you guys remember? So we have partial q partial x minus partial p partial y dA, right, equal to the line integral over the boundary of p dx plus q dy versus the integral over r of partial p partial x plus partial q partial y dA equal to the integral over the boundary of what? Q dy minus p dx. Is it? Oh, other way around. sorry, I'll get it right eventually, p dy minus q dx. These are really the same theorems. It's just the meaning. So like here, q is p, and here minus p plays the role of q down. I mean, you see the interchange? So send q to p, send p to minus q. So p to minus q, q to p. It's the same theorem, just different letters. The letters are used in a different way. But the interpretation is totally different. So the interpretation of this is that, again, the flux of the vector field is the integral of the divergence. And then guess what? You can do the same thing for what's called the curl. So if we look at the little, so this time I'm going to try to calculate the circulation of a vector field p comma q along the little rectangle. So the circulation is the line integral of p comma q around the rectangle. So this piece gives me circulation p delta x because p is the component that lines up with that. Here I get q delta y because q is the component which lines up with the vertical direction. Over here I get minus p delta x because p goes that way, but the line segment goes that way. So I get minus p delta x here. And here I get minus q delta y because q goes that way, but the line segment goes that way. So the net circulation, and of course I have to evaluate those at the appropriate points. And when I do, there's the details, just like we went through before for the other. When I look at that, that's the work done by the vector field along the rectangle, or the circulation, if you prefer, for you fluid theorists. But I don't know. I'll shut up. Anyway, so divide that by the delta x, delta y, we get the work done, the work per area, or if you like, the circulation per area done by the vector field, is the sum, or the difference of these two differences. And as the limit delta x and delta y goes to 0, well, that's a partial derivative of q with respect to x, and that's a partial derivative of y, of p with respect to y, rather. Which is to say that the change, and I used phi sub r here, but that's not right. I should really say, I'm an idiot. That's supposed to be w right there. That's a typo. Just plain old typo. That's supposed to be a w, because we just calculated w, the limit of wr over the area. So the change in the work per unit area is partial q partial x minus partial p partial y. And then if I add those up over some region, adding up, if I sum over some region, that becomes the double integral on the one side. And this motivates the net work done as being the integral of the, well, let me get to it here. So basically this motivates that the integral over the boundary of the rectangle should be equal to the integral of the difference of those partial derivatives with respect to A, the area. Now these are, neither of those things I just told you are really proofs, all right? The proof of Greene's theorem, I'll show it to you right here. So let's just prove it using standard methods of calculus. One of your homework problems, I think, is to supply the other half of this proof. So if you understand what I'm about to tell you, that homework problem is pretty straightforward. There's a chance I've removed that homework problem from the homework. I can't remember. I did? Ah. So then you guys really won't pay attention to me now. Oh well, it's a chance I'm going to take. So to prove this theorem, what I need to do is to look at a type, I'm going to look at a region which is both type 1 and type 2, which means I can either set up the area integral, using constant bounds in x, or constant bounds in y, right? I have a well-defined left and right and a well-defined up and down for the whole region. So I can either define R as a type 1 region, x going from A to B, and y is between f1 and f2, or I can define it as type 2, which means that y goes between C and D, and x is between G1 and G2. All right. And so the proof actually can be split into two pieces. Basically, one of the pieces is to prove that the integral of the p dx term works out to this, and that's what I'm going to focus on. The proof that this is equal to that is very much the same. When you put both of these things together, we have Greene's theorem. So here's the proof. I want to integrate partial p partial y over dA. So I set it up as a type 1 integration. Integral from a to b, integral from f1 of x to f2 of x, of partial p partial y dy. So what is this? Well, this is the integral over a derivative. So by the net change theorem, I just have p of the upper bound, which is f2 of x, minus p of the lower bound, which is f1 of x. And we're holding x fixed, right? So x just rides along. Then you go, okay, well, we'll split this into two pieces. It's this integral plus that integral. And then if you tilt your head and squint, you can see that this integral is nothing more than the integral along minus c2, and that is the integral along c1. Now, I need to go back to the picture. Well, I guess I could add a picture here. Well, hopefully I have that picture. So, see C2? So like C1, we have y equals to f1 of x and x equals to x from a to b. Parameterize the C1. To parameterize minus, oh, I can't tell actually. Is that that's a 1, right? Oh, yeah. I need my glasses. Anyway, this is a C2, I believe. So minus C2 is easy to parameterize. Minus C2 has x equal to x and y equals to f2 of x from a to b. Right? That would be, but that's minus C2 because I'm taking x as its own parameter, which means it increases from left to right. So when you go and you look at this formula right here, you can see what we're doing is we're taking p and we're evaluating it at the parameterization of minus C2. And this is p evaluated at the parameterization of C1. So I get minus the integral over C1 because there's a minus here. And then this is the integral of p dx over minus C2. But by properties of line integrals, I can pull the minus out like that and like that. And so I get, but C1 union with C2 is the whole curve, and there you go. That's the integral of p dx. That's half of Greene's theorem. The other half is very much the same argument. So of course, this is better than drawing little rectangles and making fuzzy arguments, but it's worse at the same time because it doesn't really give you a good sense of why Greene's theorem is interesting or true. If you really think about those little rectangle pictures I showed you a second ago, you can understand why Greene's theorem should be true. This is the rest of the argument that I didn't, this is the thing I was fudging over. So if you think about this, we've derived those little, approximation arguments on little rectangles, right? And it should be somewhat clear that if you imagine a simple shape, like a shape without holes, you can divide it up into a bunch of rectangles, right? And you can just make your rectangle smaller and smaller and smaller and smaller until you get closer and closer and closer to a real good approximation to this curvy shape, right? So then the question is, I figured out what the flux is through, say, one of these rectangles for a given vector field. What happens if you think about the flux through, say, like two of them, say this one and this one, R1 and R2? So flux through R1, there's the piece that's out there, right? There's a piece that way, this way. But then in the interior, right, the flux this way from R1 and the flux that way through R2, they're equal and opposite. They just cancel out, right? So when you sum the fluxes from a bunch of rectangles, which fill out some shape, what you're left with, because all the interior edges cancel, what you're left with is just the net flux through the edge. So that's basically the thing I was glossing over when I went to the integration. When we sum, and the same is true for the circulations. If I look at the circulation, around each one of these rectangles, any interior edge will cancel with neighboring rectangles. And so when you calculate the sum over all the circulation of all the rectangles together, what you end up with is just the circulation of the outer edge. And in the limit, as this refinement goes to infinity, we just are left with the actual edge to the curvy region. To actually do that justice would require analysis, which is just above our pay grade, all right? But I hope that's enough for you to get a sense of why it's true. All right, so let me put this away. Can you hit the lights for me? So we calculated over here, right, that the circulation, excuse me, the flux of that reciprocal vector field was 2 pi, right? What's the divergence of the reciprocal vector field? Guys, work on that. What's the divergence of that vector field? Let's work it out. Let's see here. So we're supposed to calculate the partial derivative with respect to x of x over x squared plus y squared, right? So what is that? That's 1. So what am I doing? The quotient rule, right? Thankfully, there's a symmetry here, so I can, once I do one, I know what the answer to the other should be, because it's just got x and y with the roles juxtaposed, right? So what's the divergence here then? And I'm sick of writing them, so let me call it star and star star. So it's star plus star star, otherwise known as what?
3 stars.
3 stars? Like the rot, huh? Let's see here. 0. Hey, 3 Michelin stars are pretty good. No, I actually like, I mean, when I, on occasion, get free rot food, it's pretty good. I mean, the barbecue in there is, it's there. Let's see here. It was pretty good. It was pretty good. I mean, I could use a shorter line, but anyway, it's good. It's good. Right? Wait a minute. What is up with this? Because didn't we just find a theorem which said that the integral over the disk, right, of the divergence of f was equal to the integral over the boundary, right, of f dot, well, the pdy minus qdx, right? In other words, the flux through the boundary, through the circle of radius r, which, by the way, we just worked out was 2 pi. So, excuse me, we just worked out that the divergence is 0. So this is 0. So John, do you care to explain this? No. I'm just messing with John. I saw he was messing with his phone. Which I don't. Anyway, so how can this be? 0 is obviously not 2 pi. So let me show you how to repair this. There is yet another Greene's theorem. region with hole. So if I have something like this, whee, and then there's a hole, right? Then we can say the following: the integral over the region of, partial q partial x minus partial p partial y dA, it's equal to the integral of p dx plus q dy over the boundary of R. So this is R. You're like, well, but that's just what you already wrote. Yes, but there's an interpretation that we're going to make here. What's the boundary of a region with a hole? See, there's two pieces to the boundary now. There's the outside piece. So what you have to do is imagine yourself like this little dude here walking along the edge. And if he's walking in the correct way, the inside of the region is on his left. So that enforces a counterclockwise orientation to the outer edge, right? But if you can imagine little dude walking on the inside edge, sorry, my top hats sometimes turn into sort of Pharrell hats if I'm not careful. Sorry, that comment just so 2 years ago. But if you can imagine him walking along the inside, right, he has to be walking the opposite way to keep the area on his left, right? So inside the hole, so the hole gets clockwise orientation. The outer edge gets counterclockwise orientation. And so this is actually equal to the integral over, let's say that this is C in and C out. So the integral over C in of p dx plus q dy plus the integral over C out of p dx plus q dy. Hey, what would happen if partial q partial x was equal to partial p partial y? What would this tell us? That would give us then that the integral of the vector field in the inside part with a minus would be equal to the integral of the vector field in the outside curve like this, right? But if instead of clockwise orienting the inner part, if you counterclockwise the inner part, this would actually give us that the integral for C1 of f dot dr is equal to the integral of C2 of f dot dr, where I haven't even pictured C1 and C2. So basically use the same argument. Suppose C1 and C2 are both counterclockwise oriented, and you've got that, partial xq is equal to partial yp in here, in between them. If that's the case, then we can deform the line integral along C1 to the line integral on C2. They're just equal. This is the deformation theorem. So can anybody explain this paradox? Why is 2 pi not 0? Because I really want to start my weekend. What about you? So there was fine print. There was fine print in Greene's theorem. Well, I haven't written it today, but last time I mentioned that the vector field has to be continuous in and near the region, right? Is this vector field continuous at the origin? It's not. What's the value? The magnitude of this vector field is 1 over the radius, right? What happens to that magnitude as you go to the origin? It's undefined, right? It becomes infinite. So that's what's the problem here. Greene's theorem does not apply because this vector field has violated the terms and conditions of Greene's theorem. It is not behaving at the origin. However, you could prove that if you look at any shape like this, C1, here's my CR, the integral around C1 of f dot dr is equal to 2 pi for any curve which encircles the origin. It could even look like this. That curve, let's say C3, clockwise oriented C3 around the origin, that can be deformed to the unit circle, into a circle of radius r, right? You could look at the circle of radius r right here. And between those two, you can prove that for this reciprocal field, partial q partial x is equal to partial p partial y, so the line integrals are equal, any crazy loop that contains the origin will have a circulation of, will have a flux of 2 pi, for our example. Anyway, we'll try to talk more about this Monday, and I will get back to my daily quizzing. I know you're missing it. So, have a good weekend.